In this video, you will learn about different CNN architectures. Popular architectures include LeNet 5, AlexNet, VGGNet, ResNet. We will go over a few of them in this lesson. We will also cover transfer learning. One of the first CNNs was proposed by Jan LeCun and others in 1989. The most successful use case of the LeNet 5 is the MNIST dataset of handwritten digits. LeNet receives an input image, normally a grayscale image. It uses a 5x5 filter with a stride 1 and results in a volume of 28 by 28 outputs. The next layer is a pooling layer with 14 by 14 outputs. It repeats itself with a filter and pooling layer until it gets to the fully connected layers, where it flattens to create 120 neurons and another with 84 neurons, while using a sigmoid activation function to produce an output. For a while, CNNs dropped out of popularity for image classification, and support vector machines became the default standard. If you want to compare any image classification methods, you compare the classification accuracy on a dataset. ImageNet is a benchmark dataset. That is, this is the one that everyone uses to see who has the best image classification method. Here is an image of the top performer every year. Prior to 2012, a method using SIFT, a feature like HOG, took the top spot with 51% accuracy. After 2012, AlexNet smashed this record with 63.3% accuracy. This jump was so large, everyone started using CNNs for image classification. Here is a block diagram of AlexNet. We see the network has lots of parameters. We see convolution kernels are of different sizes. If you recall, more parameters means you require more data. We see the first convolution kernel layers are of shape 11 by 11 with 25 channels. This is quite a large number of parameters. The VGG network is a very deep convolutional network that was developed out of the need to reduce the number of parameters in the convolution layers and improve on training time. It also showed in general that deeper networks performed better. VGGNet has multiple variants like the VGG19 and the VGG16, where 16 stands for the number of layers in the network. Here, VGG16 is pictured next to AlexNet. We see it's much deeper. The key insight gained by the VGG networks is we could replace the larger kernels in the convolution layer by stacking convolution layers with 3x3 kernels, keeping the same receptive field while reducing the number of parameters. This also reduced the number of computations by reducing the number of operations in the convolution layers and decreasing the feature map size. As CNNs got deeper, the vanishing gradient began to become a problem again. ResNet helped solve the problem by introducing residual learning. Residual layers or skip connections allow the gradient to bypass different layers, improving performance. We can now build much deeper networks. Here is a 32-layer network from the paper Deep Residual Learning for Image Recognition. Transfer learning is where you use a pre-trained CNN to classify an image. Instead of building your own network, you can use the CNN architectures we discussed. Pre-trained CNNs have been trained with vast amounts of data. We will cover the simplest method, where we replace the softmax layer with our own softmax layer. The number of neurons is equal to the number of classes. We then train the softmax layer on the dataset we would like to classify. The input dimension of each neuron in the softmax layer is equal to the last number of neurons fully connected layer. The pre-trained model can be thought of as a feature generator. Depending on the size of your dataset, you can use SVM instead of the softmax layer. Check out the labs for more.